Thank you, and thank you for having me here. It was really great to talk with people the last couple of days, and yeah. So I'm excited to tell you about tree spaces in tropical geometry. And I'm Shelby. I'm a postdoc at the MPI in Leipzig. So first, I want to tell you a little bit about what is a tree space. So in a tree space, each point or vertex represents a tree, so just a graph. And there's kind of two classes of tree spaces that people think about. So one of these discrete ones, so graphs of trees where each vertex represents a tree, and trees that are most similar are connected by edges. Usually those edges represent some tree operation that turns one tree into another. And there's also these continuous spaces. And this one that's displayed here is the BHV space. It's one that's widely used in biology. And you'll notice that it's a polyhedral fan. And this is also a tropical space. So in this talk, for me, tropical varieties will always be polyhedral fans. Yeah. And so I'll only talk about continuous spaces. There's two tropical ones that we're going to be interested in, the tropical Grassmannian of rank 2, and the space of ultrametrics, which is also known as the tropicalization of the complete graph and the tropicalization of M0n. It's a forest space. So you kind of take you take the BHV space and you kind of compactify it by adding in forests at the boundary. Yeah. Yep, something like that. Yeah. Yeah, so there's many tree spaces, and we'll focus on the tropical ones. And there's also many metrics that you can choose. So in the graph, usually you take a shortest path metric. There's a metric for this BHV space, and there's also two tropical metrics. And this distinction is going to be really important in the first half of the talk. And yeah, then there's a metric for the walled space, and there's probably many more also. And one problem with tree spaces is that they're not classically convex. So you can see this space here, it's definitely not convex. It's a bunch of cones that are glued together, and they're low dimensional, but in a very high dimensional space so that they don't intersect each other. Like they don't pass through each other. And this creates problems when you're trying to study statistics of trees, because most of the methods we have for statistics rely on the space being Euclidean. And this is definitely not. And so in some sense, looking at these tropical versions is really natural because this second tree space is tropically convex. And we don't really know how to do statistics on this space either, but we took these problems that, these statistical methods that we know in Euclidean space, and now we can study them in tropical space, and we have to have new interpretations of them. But all of these problems become kind of polyhedral geometry problems. Yes, so in the title, I said these are from phylogenetics and physics. And so in the first half, I'll tell you about tree spaces in phylogenetics. So a phylogenetic tree on n leaves looks like this. This is a tree on 4 leaves. And it can be rooted or unrooted, and I'll make sure to specify when we're looking at rooted trees. It's a metric graph, except that I also allow negative edge lengths on the pendant edges, or the edges that are adjacent to leaves. And there's no degree 2 vertices. And the topology is the underlying structure of the graph with the leaf labels, but forgetting about the edge lengths. And with all these assumptions, if I define this tree metric to just record the pairwise distances between leaves, I can also recover the tree from that. So here, this tree's vector, distance vector, or tree metric, records the distance between 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. And you just add up the lengths of the edges between 1 and 2 to get the distance between 1 and 2. So add it up. Oh, yes, you're right. Okay, yes, this should be 1.8. Wonder if all of these are off by 0.1. Okay, I'm sorry. This was something must have. Okay, so anyway, maybe ignore this, but you can add up the distances to get this distance vector. And Yeah, so because we can uniquely recover the tree from this vector, we'll just identify the tree with this vector in Rn choose 2. And this is going to form the space of trees, are the vectors that arise this way. Okay, and here's the problem that we want to answer or address. So let's say we're given some biological data on N taxa, and here taxa means like species, cells, or individuals. And usually that data comes in the form of DNA sequences. And from that, we want to reconstruct a tree that describes the evolutionary relationships between those species. Now, there's a ton of ways to do this, and they usually disagree even when you give them the same input data. And it's also really difficult to evaluate which ones are working the best because we don't know the ground truth about the tree. And in particular, we rarely have this historical data on the interior nodes of the tree. So usually we only have the data at the species leaves, and there's no way to check did this method recover the right tree in my experiments. And so one solution to this is to use a consensus method. So I look at a bunch of different reconstructed trees that were reconstructed from different methods. And I try to see where did they agree on the evolutionary relationships and where did they definitely say that this relationship couldn't have occurred. And from that, I can construct a consensus tree. And so in using tropical geometry, we're going to construct a consensus tree by averaging these trees. And if you take a bunch of tree vectors, there's no way that you can just compute the Euclidean average because it's not a Euclidean, it's not convex. So you would get a vector that doesn't even represent a tree. But in tropical geometry, this is possible because it's tropically convex. Okay. So like I said, there's these two spaces of phylogenetic trees that occur in tropical geometry, and you might have seen both of them. So in the tropical Grassmannian, that parameterizes realizable linear spaces, and the trees occur as literally tropical linear spaces. And you'd see that there's this nice picture. You have a matroid subdivision, and your tree is dual to that. And the problem is that this space is not tropically convex. On the other side, we have trop M0n and the tropicalization of the complete graph. It's also known as ultrametric space. And here, this is going to be the distance vectors of rooted trees that are equidistant. And that just means that the distance from the root to any of the leaves is the same in every tree. So you see here, this is the space of equidistant trees on 4 leaves. And each of the trees has this root up here, and the distance from the root to each leaf is the same. And these tree metrics satisfy this additional rule that the maximum of the distances of any triple of distances, or the distances on any triple of leaves, is achieved at least twice. And this is a tropical linear equation. And so this exactly defines the tree metrics that are equidistant. And so this space is a tropical linear space. And this was first done by Ardilla and Clivens in their paper on the Bergman fan of the graph and the space of phylogenetic trees. Yeah, and so since it's a tropical linear space, it's tropically convex. And there's also some results that say that we can do statistics on this space like we can on other spaces. I won't go too much into that, but more focused on this averaging problem. Okay, so I said it's tropically convex, and now I want to explain a little bit about what that means, or what that gets us. So the max tropical convex hull is a set of all tropical linear combinations using the max operation. And there's this weird switch, or this weird combination of min and max conventions, that the max tropical convex hull is bordered by the min tropical hyperplanes. So here's a picture of a tropical, okay, so this is a max tropical triangle. And this is a min tropical hyperplane arrangement. And the max tropical triangle consists of all the bounded regions of the min tropical arrangement. And it goes the other way too. So you can swap min and max. And each of these cells is a classical polytope, and it's also max and min tropically convex. That's a polytrope. And if we take a bunch of equidistant trees as our vertices, then by the tropical convexity, the tropical polytope is also going to be contained in the tree space. So that means that every point in there can also be interpreted as a tree. And for the relative interior of each of these cells, or each of these regions of the hyperplane arrangement, those don't cross the cones of the tree space. So in the interior of each cell, you only get one possible tree topology. So here's an example of a tropical line segment in the space of equidistant trees on 4 leaves. And so each of the edges here that we saw in the previous graph, that's a 2-dimensional cone in the space. And you can see that this line segment, or this tropical line segment, is a concatenation of classical line segments. And whenever you stay within one classical line segment, you're within one cone. So you can't cross the boundary of a cone without concatenating like another line segment. Okay, so the way that we're going to average our trees is using Fermat-Weber points. So these are the median. This is a way of taking a geometric median of your data. And the Fermat-Weber points are going to be all the points that minimize the average distance to your data, or the sum of the distances to your data. And usually they're not unique, so we'll consider the whole set of Fermat-Weber points. And this was studied in with 2 distances previously in the tropical setting. So it was first studied for the symmetric tropical distance, which is this one. So you take the max of all the coordinates, the differences of coordinates minus the minimum differences between coordinates. And you're working in the tropical projective torus in both these cases. And this was first studied, I think, around in 2018 by Sturmfels, Lin, and Yoshida. And they found that the tropical Fermat-Weber set in this case is a polytope, but it might not be contained in tree space. And this is a more refined result. That's the newest version. So the Fermat-Weber points form a polytrope, but they can lie outside of the tropical convex hull of the data. And so they can also lie outside of tree space. And in the asymmetric case, you get something really different. And this was this asymmetric distance was introduced by Comaneci and Josvig. And if you look at this asymmetric metric, then actually the Fermat-Weber points are a cell of the tropical convex hull. So it's one of these regions of the tropical hyperplane arrangement, and it's one of the bounded ones, so it actually belongs to the tropical convex hull. And so this allows us to get Fermat-Weber points that will actually compute a tree at the end of the day. Okay. And then, yeah, so inspired by this paper of Comaneci and Josvig, and jointly with Mays Curiel, I worked on weighted tropical Fermat-Weber points. So instead of just taking as input data your points, we also add some weights to the points. And now the Fermat-Weber points are the ones that minimize the weighted distance to your data. And again, we're studying the whole set of Fermat-Weber points because this is still not unique in general. And we found that the weighted Fermat-Weber points are still a cell of the tropical convex hull of the data. And in fact, if you give me any data and any cell of that tropical convex hull, then I can give you some choice of weights that will make that cell the Fermat-Weber set. So this shows that these weighted Fermat-Weber points are kind of maximally expressive in the sense that you could get any part of the tropical convex hull as your Fermat-Weber set. Yes?
About the slide. I can also ask in this slide. So when you say that you get a cell, given by this point, then the tree is the combinatorial type of that cell.
Yes, the interior of that cell. Yes, and I'll have it a bit later also, the exact definition. Yeah. Okay, yeah, but the key here is, yeah, using this asymmetric distance, the problem becomes a lot simpler. And it becomes a purely like polyhedral geometry problem. And I'll give you a bit of insight into how that works now. So the key to this is the identification of the tropical projective torus with the space that's perpendicular to the all ones vector. So every point in the tropical projective torus has a representative in this hyperplane. And when you use those representatives to write the asymmetric distance, what you get is just a max of a bunch of things. Because remember, there was a sum of the coordinates here. But when you assume that the sum of your coordinates is 0, this part just goes away. And so now you can write this distance as a tropical polynomial. And the sum of the distances is a product of these. And the tropical vanishing of this set is the tropical hyperplane arrangement with this hyperplane centered at the data points. And the tropical hyperplane arrangement, the regions govern the regions of linearity of this function f. So if we want to optimize it, the optimum is going to be achieved on one of those regions of linearity. So we're going to study the tropical hyperplane arrangement. And yeah, this identification is really compatible with the tropical vanishing set as we normally draw it of a homogeneous polynomial as we normally draw it. So I'll show you in a couple slides what exactly I mean by this. So in the weighted case, so the previous one was all done by Comaneci and Josvig. And in the weighted case, weighting the distance just turns into a tropical power. And so we get our new function to minimize. And the tropical vanishing set is still the tropical hyperplane arrangement centered at V1 to Vm. So it doesn't change with the addition of the weights. And that's just because if you, doing this tropical exponentiation doesn't change where the minimum is achieved twice. Okay, so this works for this picture will work for any this first picture will work for any tropical polynomial. And then this last picture is specific to this example that we're looking at with a product of tropical linear equations. So if we look over here, this gray picture is the graph of f when it's restricted to x being in this space that's perpendicular to the all ones vector. And this picture below is in the tropical projective torus. But because all of these cells in both cases have this, so the cells down here have a lineality space that contains the all ones vector. And the cells up here have a lineality space that's not exactly the all ones vector, but it could have some slope extra. But when I do a restriction up here and a quotient down here, it preserves the correspondence between the cells here and the regions of linearity up here. And then in the dual picture, that's where we see all the slopes of the faces here as points in the plane. So the Newton polytope encodes the possible slopes of this function. And if you have a convex function and the minimum exists, then the minimum will be achieved on the part of the function where you have a constant hyperplane tangent to it. Okay. So there's nothing, this is like a pretty straightforward statement, but that just means that since we're restricting to the space that's perpendicular to the all ones vector, any supporting hyperplane that has a slope that's a multiple of all ones is going to be constant on that space. And that's going to be, if that's a supporting hyperplane of one of these faces, then that's the face that's going to achieve the minimum. So what I'm looking for here is the point in the Newton polytope that is a multiple of the all at once vector. And you can see that marked with a star over here. And whatever cell that occurs in, the dual cell over here is going to be the one that achieves the minimum. And I've tried to color code it also so that you can see the duality here. So the blue point here is dual to this blue triangle here, and that's over here. Okay. Yes, and yeah, finally, so changing the weights didn't change anything in this picture, but in the dual picture, we do change the slopes of each of these components. And that corresponds to a rescaling of the simplices in this subdivision, or the cells in this subdivision. And so this result says that we can rescale these cells so that this zero hyperplane, that slope, is in whatever cell we want it to be. Okay. So everything that I just said will work for any kind of data in the tropical projective torus. It doesn't need to be tree data, but since it is in the tropical, the Fermat-Weber points are in the tropical convex hull, it gives this nice application to phylogenetics. And again, everything we did here was inspired by the approach of Comaneci and Josvig. So they take the unweighted Fermat-Weber points and they compute the classical average of the tropical vertices of the Fermat-Weber set. And yeah, so you can remember you can compute the classical average here and it'll still remain in tree space because each of the cells is actually a polytope also, like so it's actually classically convex. And yeah, they show that these are both good trees and that they can be computed quickly. So every tree in the tropical convex hull is Pareto and co-Pareto on rooted triples. And I'll explain what that means now. So a rooted triple is just a set of 3 leaves, and you tell me how those leaves are split in the tree space. So which of the least common ancestors of each of these 3 is the highest. So here I bar jk means that j and k are closer to each other than they are to I. So it looks like any of these examples. And for a consensus method to be Pareto on rooted triples, that means if the rooted triple occurs in all of the samples or all of the input trees, then it must occur in the consensus tree. And co-Pareto means that if a rooted triple occurs in the consensus tree, then it also has to be coming from one of the trees that you put in. So you can't just make up new relations. And if all the trees agree on something, then it has to be included. And so yeah, the result here was quite general. So every tree in the tropical convex hull is Pareto and co-Pareto on rooted triples. And so when we define this analogous definition using the weighted Fermat-Weber points and the weighted Fermat-Weber set, that is also automatically Pareto and co-Pareto on rooted triples. The second big part of their paper was that the tropical consensus tree or this Fermat-Weber set can be computed in strongly polynomial time. So it's quadratic in the number of samples and n log n in the number of leaves. And that's something that we're still working on here. So because the weights introduced some asymmetry in this problem, it wasn't clear right away if this polynomial time algorithm could be extended.
Have you tried weighting the average?
Oh, here also, like.
Yeah, like taking the average with weights. I don't know.
Yeah, I didn't think about doing that actually. Maybe it'd be, yeah. So I'm not sure. Okay. Are there any other questions before I move on to another topic? Okay. So now I want to talk about tropical geometry and tree spaces in physics. Okay, and on this first slide, I have the definition of a variety that comes up a lot in physics, and sorry, or class of varieties. But you shouldn't spend too much time trying to understand this definition because I won't use most of this. This is just so that we have the full definition here. So the ingredients are you start with a flag simplicial complex and some integers, and you build an affine variety that's defined by these equations. And the important parts of that, sorry, you have trinomial equations defining this. And this is not a complete intersection at all. So the dimension should be the dimension of the simplicial complex that you start with plus 1. And so the condition on this dimension, so there's some dimension conditions, and those really greatly limit the types of varieties that you can build here. And so for two-dimensional binary geometries, those come from one-dimensional simplicial complexes, flag simplicial complexes. And there's only 4 known examples. So you can build one from a square, a pentagon, a hexagon, or an octagon. And these correspond to the cluster varieties for the 4 rank 2 root systems. And there was this observation. Oh yeah, so and in higher dimensions, you can continue building stuff from root systems. The generalization for type A, or M0n, is the dual associahedron as your simplicial complex. And for type C, it's the dual cyclohedron. And if you haven't heard those words, I'll also explain those a bit later. But there's also other varieties in higher dimensions that you can build. Okay, and so this other project started with the observation that the positive tropicalization of one of these varieties looks like the simplicial complex that you started with. And yeah, just to make sure we're all on the same page, I just want to make sure to tell you what I mean by signed or positive tropicalization. So in the regular tropicalization setting, I'm thinking of tropicalizing an ideal, and specifically one of these binary geometries. So this definition is a bit more specific than one you might normally see. So I start with a field like the Puiseux series, and I have an ideal, which I'm only going to think of it really as having real coefficients. So not even complex coefficients and not so this is the constant coefficients case. And this defines a very affine variety. Then the tropicalization is going to be all the weight vectors that give me an initial ideal that doesn't contain any monomials. And this is going to result in a polyhedral fan. And the intuition for something belonging in the fan is that a weight belongs in the fan if some lift of it, or if everything in the ideal could vanish at some lift of that weight. In the positive case, the positive Puiseux series have a bit of a unintuitive definition. So we take all the Puiseux series that start with a positive real coefficient, but the rest of the coefficients are also allowed to be complex. And a positive tropicalization means that we take all the weight vectors so that the initial ideal doesn't have any equation or any functions, any polynomials with only positive coefficients. So this is telling us that if I took a lift of my weight that had all positive initial coefficients, then it's possible that all the functions in I could vanish at it. If I had a function that had only positive coefficients, and I plug in a point that has only positive initial coefficients, then there's no way that that function could vanish. And in the sign case, we also take as input a sign pattern, which is just a n-tuple of 1 and -1. And it acts on the polynomial ring by changing the signs of the variables. And the sign tropicalization is basically going to be the definition of positive tropicalization after this action by the sign pattern. Okay, so here's an example. I have a weight W1, W2, and a lift of it looks like a piezo series that starts two piezo series. So X equals A TW1 and Y is B TW2. And in the tropicalization, so I get these initial ideals, and I leave out the ones that are monomials. So I get these three rays. In the positive tropicalization, I leave out the monomials because those all have constant signs. And I also leave out this ray because it only has positive signs. And in this sign tropicalization, I choose the sign of X to be negative and Y to be positive. And so after I act by the sign vector, now this one has mixed signs, but this one doesn't anymore. They're all negative signs. So I get rid of that ray. Okay, and here's an example that's pretty well known. So again, the tropicalization of M0 n+3 is the space of phylogenetic trees on n+3 leaves. And it looks like the fan over the Peterson graph. And okay, and the positive part, so one of the positive component is this pentagon around the outside. And I've drawn on each of the vertices these labels of a pentagon with one diagonal. And so the dual associahedron has vertices whose labels are n-gons with one diagonal. And you connect them if the diagonals are compatible in the sense that they don't cross. So they define a subdivision. So in this case, the associahedron is just this pentagon around the outside. And that gives us the positive tropicalization. And the trees on each of these edges are the planar ones in some order. So I've made an arbitrary choice that I'll choose the order 1, 2, 3, 4, 5 to be positive. And then the other 11 sign patterns give you also a 5-cycle. And yeah, so there's 12 5-cycles in this graph. And they glue together when a tree can be represented in 2 sign patterns. So here, this tree, it doesn't matter if I switch in the planar embedding where I draw 1 and 2. And so that gives me another sign pattern that this tree is going to belong to. Yeah, and so this was a nice example. And this is joint work with Igor Mocklin. And we wanted to know, does this happen in other types? Do you get a similar picture with trees? Okay, not sure if this would happen. Okay, yeah, so the next case we tried was type C. So we already kind of knew that the positive tropicalization was going to be the fan over the dual cyclohedron. And the dual cyclohedron has as its vertices 2 n-gons with sets of symmetric diagonals. So in this case, all of the diagonals are required to have a central symmetry. So there's 3 diagonals that are long diagonals, and those are already centrally symmetric themselves. And then there's 3 sets of symmetric diagonals where you get 2 diagonals here. Yes, and again, they're non-crossing, so that's how you connect them. Okay. And again, we choose some arbitrary order that we want to be positive. So I chose 1, 2, 3, -1, -2, -3. And this order has to be centrally symmetric. So if I rotate it 180 degrees, I should send 1 to -1, 2 to -2, and 3 to -3. And so this results in centrally symmetric trees. And the important part is that centrally symmetric trees need to be dual in the way that I've drawn them here to a centrally symmetric subdivision. And it's not enough for the tree to just be centrally symmetric. So it's really a statement about the dual subdivision. And right, so there's 4 centrally symmetric dihedral orders on 3 + 3 elements. And you can, if you want, you can try to figure out what those are. But there's 16 signed components of this variety. So the question is, what are the other 12 signed tropicalizations? What do they look like? Does anybody want to guess? Okay. Okay, yeah, here I had a better picture of this. Okay, so yeah, here, right, this tree doesn't care what order -1 and 3 are drawn in, but I can flip both of these at the same time, and then I get another centrally symmetric dihedral order, and that gives me a different 6th cycle, and I glue them together where the trees agree, but the subdivisions might not agree. And yeah, so you can see the 4 6 cycles. One's around the outside, and then there's one here, and then one up there, and one here. But that doesn't even cover all the edges of this graph that I've drawn. Okay, so yeah, it turns out that the other 12 are axially symmetric dihedral or axially symmetric trees in some dihedral order. So yeah, and so essentially this is giving us a picture almost in type A again, right? So we have 12 pentagons. And so this 5 cycle is an example of one of them. And it's going to be the fan over the dual associahedron. And it's, yeah, not clear from that picture how you do that, but I'll explain with these 2 trees on the side. So, yeah, so this, okay, one slide. Okay, so right here, these 2 trees are dual to a centrally symmetric subdivision. And any centrally symmetric subdivision, I can draw a long diagonal through it that either is a long diagonal of the subdivision, or but at least it doesn't cross any of the non-long diagonals, any of the short diagonals. So in this case, right, these 2 trees here, they share this long diagonal. And by cutting the polytope there and flipping one side, now I have an axially symmetric subdivision. So an axially symmetric subdivision has a folding across the axis. And there's going to be 5 trees that are axially symmetric in this planar order. And you can see that in kind of a weird way. So you add a vertex to this axis of symmetry, and now you have a 1, 2, 3, 4, 5 gone. And that brings you back to the previous case with AN. Yeah, and the other thing that we realize is there's this map that looks a little bit strange in these coordinates, but it gives you each of these cones as a tree metric, the same way that you could do for M0n, the M0n picture. But it's just this weird change of coordinates that it looks like a bit of a string. Yeah. Okay. And so this was a computation for C2. And we did this using Macaulay 2 and some elbow grease. It was a bit more than Macaulay 2 could handle alone. But yeah. And so, yeah, but what we haven't proved yet is that this is true for higher dimension also. So this is our conjecture for the space of, for the tropicalization of MC n minus 1. We think that it's the complex of, it's the fan over the complex of axially symmetric trees on 2n leaves. And the sign subfans either look like are either given by centrally symmetric dihedral orders, and they're the fan over the dual cyclohedron, or they're given by axially symmetric dihedral orders, and they're the fan over the dual associahedron. And yeah, that's it. So thank you for your attention. And yeah, if you have any questions.